This is question 10 from the June 21 paper. Thanks again to Leo for highlighting this one as one to go through. It'll help us to revise quite a lot of stuff actually from the electricity unit. So let's dive in. First of all, we've got some overhead power lines and a national grid. And it says, explain the advantage of transmitting electricity at very high potential difference. And this question comes up a lot, and you should immediately think, do you know what? If we've got high potential difference, then we've got very low currents. Why is that a good thing? Well, that's because we then lose less energy to the surroundings. So I've said less thermal energy dissipated or less thermal energy transferred to surroundings. That's fine. And so what? So the efficiency of the power transmission increases. So we're going up to 400,000 volts, getting much lower currents, less heating, more efficient, not losing much of the energy that we need at the other end. So we don't want to lose energy just warming the cables up. 10.2 is tricky, so let me explain it. Okay, it says it's dangerous for a person to fly a kite near an overhead power cable. Figure 14 shows a person flying a kite. The person could receive a fatal electric shock if the kite was very close to, but not touching the power cable. Why is that? Now, this bit of physics is all about electric fields. Now, in the same way that when we get a magnetic field, we can draw magnetic field lines going from north to south. If we've got a potential difference between two plates, for example, on this little diagram, we can draw an electric field with electric field lines going from positive to negative like this. So there's a region between those called an electric field that will influence a charge. It will put a force on a charge. But the point of this is, if we've got a high voltage power line and we've got the earth, the electricity will jump, or the charge will try and jump to earth like a lightning bolt. Now, if it's really high, then you would actually get a lightning strike. But if it's just high and there's plenty of air in between us and the high voltage line, then the insulation of the air is enough to stop it from what we call arcing across or just discharging across that gap, because air is a good insulator. But if you put a kite very close to it, you've got a lot less air to jump across. So what will happen is the charge will jump across the gap and it will then flow down the kite through the buoy or whoever's flying the kite and electrocute them. So it will pass through their body because it's now got a path to earth. It's jumped across the high resistance bit, which is the air. It's gone through the relatively low resistance bit, which is the string and the human, and then it's gone into the ground. So that will give them a fatal electric shock. Not a nice idea, but it's an important idea to understand. So I've written here, electric field between high voltage and earth. If it's big enough, it can cause air to conduct and like lightning. So let's explain that in words then and look at the mark scheme as well, which is over here on the right hand side. First of all, you're going to point out that the electric field strength is very high. Therefore, air can become ionized. So you can break down the insulation of the air and you're basically ripping the electrons off and then they're free to flow. Then they will flow to earth. But just saying it becomes ionized is great. Okay, so you're charging the air basically. And then I've written the spark jumps across the gap to the kite and conducts charge through the person to earth. And if you look at the right hand side that's on 10.2, that's basically what it says there. Electric field strength is very high, causing the air to become ionized, conducts charge to the person or to the earth. Okay, so there's a few different ways of writing that on the right hand side. But get your head around this idea that there's an electric field because you've got a high voltage, a high potential difference between the high voltage line and the earth. In the same way, like I said, you could have it between the clouds and the ground, and then you get a lightning strike in a storm. The next one, scientists investigated how the potential difference needed for air to conduct charge varies with distance between the cable and air. And what they've given us is the potential difference, 200,000, 400,000, 600,000, 800,000. And then the distance between the cable and earth, and it goes up linearly like this. And then it says the data in figure 15 gives the relationship between potential difference and distance when the air is dry. So this is for dry air. When the humidity, so we're now getting more moisture in the air, increases, the air becomes a better conductor. Water is a better conductor than air. So if you get damp air, it's going to conduct better. Draw a line on figure 15 to show how the potential difference changes with distance if the humidity of the air increases. So you know it's either going to go like that or it's going to go like that. Now, what you need to remember is that if you've got a lower, well, if it's damp air, then a lower PD is needed because the air has become a better conductor. So it's actually got to go below the line, again, linearly and passing through 0. 10.4, just to finish off, figure 16 shows a cross-section through a power cable. We've got steel core, that's to give it strength, and we've got aluminium around the sides. A 1 metre length of single aluminium wire is better conductor than 1 metre length of steel wire. The individual wires behave as if they are resistors connected in parallel. Explain why the current in the steel wire is different to the current in a single aluminium wire. Well, the potential difference across both is the same. That's the first mark. So if you were to put a voltmeter across here, then you'd get the same reading across all of them. Okay, they'd all be the same potential difference. But the steel's got a greater resistance, which means it's going to have less current. So that's what I've written here. But the resistance of the steel is greater, so there is less current in the steel. So hopefully that's answered question 10 for you. I'll keep doing these as you request them, or as I think there's a bit we need to go through in more detail. But that's question 10. I did question 9 on a previous video about pressure. But thanks, Leo, again for highlighting these. If you've got any others you want highlighting and me to go through, then let me know.